Hello everyone, this is a short video just to show you the big picture of Fourier transform. So the idea of the Fourier transform is that it allows us to see the frequency content of a given signal. Assuming that I have a function f of t that is available, which varies over time, as I show you here outlined in blue, I'm going to multiplicate this function with a complex exponential in a given frequency omega. So I'm evaluating each omega, which means different frequencies that are present at this function f of t. Although this complex exponential here can scare some people, it is actually a simplification, a more compact way to write a sum of a cosine and a sine. So don't be afraid of that. This is just me saying that I'm multiplicating this f of t with a cosine and a sine at the same time. So instead of using this representation here, I could just divide it in two parts. However, in practical examples, in practical computations, I don't have access to the whole function, but I rather have access to the samples that are taken from this function over time. So in fact that I actually have are just points that are sampled, and I'm going to call this sequence of examples an array of n samples. So for n samples, I'll have to compute not the continuous Fourier transform, but the discrete Fourier transform. Note that I change from omega to k and from t to n here to indicate that I'm working now with the discrete. Because of the fact that I don't have the function anymore, I cannot integrate from minus infinity to infinity. So what I need to do is to sum from 0 to n minus 1. In practice, then I'm going to evaluate values of frequencies from 0 to n minus 1. As in the case of the continuous function, what I'm actually doing is computing two parts, a real part, which is associated with the cosine function, and an imaginary part, which is associated with the sine function. Note also that because of the fact that I'm now in discrete and finite case, the omega here in the complex exponential becomes k over n. I can see each one of these values that I compute, that I evaluate, as a vector in a real and imaginary plane, in which I show you a of k as a real part of the signal and b of k as the imaginary part of the signal. This vector here can tell us some important information about that specific frequency in the signal. By evaluating f of k on different values of k, we can obtain the amplitudes of cosines, which is the real part, and sines, which is the imaginary part, so that we can reconstruct f of n if needed. Here I have two important information that I can extract from the DFT, which is the magnitude of the vector, which tells me the amplitude of this frequency, and the phase angle, which tells me how much this specific frequency is shifted from the sine function, from the base function. Another important thing is that cosine is a symmetric function and the sine is an antisymmetric function, and because of that, values of k after n over 2 start to repeat. This means that when I start to evaluate the different values of frequencies starting from 0 here, I observe lots of different amplitudes over time, and by the time I reach the middle of my n samples, which is in this case 100, I start to observe repeated values that are symmetric with respect to the middle, to n over 2. That's why we often just show half of the values. This N over 2 maximum frequency that I can observe has an important relationship with the Nyquist-Shannon theorem of sampling that I'm not going to cover in this lecture. Another important aspect of this doing Fourier analysis is that when I start to, because I start to measure at k equals to 0 and stop at n minus 1, these abrupt changes here in the beginning and the end of the function can be considered high frequency content, and it often hampers the analysis. And what I'm showing you here is the logarithm version of the Fourier magnitude, and as you can see, there are lots of frequencies here that are not present in the signal, and it can somewhat hamper the analysis. So I can use a windowing function to obtain a signal that increases its amplitude more slowly from the beginning and going through the end of the function. In this example, I'm showing you a Gaussian function that I use to filter or to multiply with each sample over time, and then what I have is a function that starts slowly increasing its amplitude and then decreases its amplitude that goes towards the end. And it allows me a much more clearer analysis in terms of the frequencies. In this case, the two peaks regarding the frequency 50 and 80 are clearer than in the previous example here. Let me show you an example in the code. What I have here is basic code importing NumPy and matplotlib, and then I'm creating a space of discrete samples with 100 samples over time. The sine function has 20 a value of 20 for its frequency, and the cosine 65, and the cosine is weighted so that it has half the amplitude as the sine. In order to compute the Fourier transform, I can use FFT, which is at SciPy FFT pack. So from SciPy FFT pack, I can import FFT. And because, here I'm computing FFT, which is the DFT, a fast version of the DFT. And I'm going to plot, so YF. And I'm just showing you the amplitudes, so the magnitudes of this Fourier transform. I'm creating another space of discrete samples here, but I'm creating it just for half of the values, so with 50. And because of that, I'm just going to show the first 50 frequencies. So I forgot to multiplicate here for each sample. So I had to build the function by creating samples over time, which is codified here with this X-array. Here I can see clearly that there is a peak on 20 and a peak on 35 or so. That is because of the fact that I was just sampling on 100 and I have a frequency that's higher than half of this value. So I'm actually not observing the exact value of frequency, but something that it's showing me something that is actually wrong. So that's why I commented about the maximum value of frequency. So if I'm sampling on 100, the maximum frequency that I can analyze is 50. Let us increase this sample to 200 or maybe 300, and I will show up to 150 here. And now, as you can see, I can observe the value 65. So this is how you compute FFT, or the Discrete Fourier Transform, using Python and SciPy. And I hope that will help you complete your homework assignment.